Professor Clements with you, and today we're going to discuss the distances to stars and a little bit on the brightness of stars. The distance is a very important property to know about a star. We need to know the distance to really understand how much energy the star is emitting from our measurements of the brightness of the star. So how are we going to determine that distance? We can't take a trip easily to a star and go a certain number of miles per hour for a certain number of hours. Distance equals rate times time. Well, that's not going to work for us. We're going to have to discover a different way. And then the distance to the star does change the brightness. If two stars have the same brightness, the one that is farther away will be the dimmer star. So let's take a little activity here on a map of the United States. If you'd put the sun, a little dot at your location, I'm doing this in Nebraska, and if we considered the sun to be the size of your little fingernail, if you have a sort of standard size for your little fingernail, it turns out that the closest notable star is Proxima Centauri. It's going to be about 250 miles away. If the sun is the size of your little fingernail, this star is going to be 250 miles away. Now, I've worked out the distance in miles for stars on this scale. So Proxima Centauri, you'd plot 250 miles away from eastern Nebraska, if you want to do it for eastern Nebraska. Sirius would be 500 miles away. Procyon, 675 miles away. Procyon is in the constellation of Canis Minor, above Canis Major, where Sirius is. The star Vega, it's more of a summertime star, 1,500 miles on this scale. Regulus, 4,600 miles away, the star in Leo. And then Polaris, our North Star, 25,700 miles away. And again, recall, we're doing this with the scale of the sun is the size of your little fingernail. So there are tremendous distances, and there's never been a spacecraft reach another star. In the 1970s, the Voyager spacecrafts were launched and made very good measurements of the properties of planets in our solar system and had enough velocity to escape the sun's pull of gravity. However, it's going to take about 60,000 years for the spacecraft to reach a distance of the closest star. It's not aimed at a closest star, so it'll just be an empty space when it gets to that distance. But 60,000 years, that's our best spacecraft speed. It takes 60,000 years to get to the nearby star. It's the tremendous distances between stars in our galaxy and in all galaxies. So just want to leave you with that little thought. Here's a little plot of nearby stars. Some of the major ones I'll point out here. Sirius again in the constellation of Canis Major, and Procyon over here in the constellation of Canis Minor, and there's some other stars plotted on here that aren't quite as famous as those, but this is a mapping of the nearby region of our galaxy. And again, if we would try to get to this first band is at 5 light years, and 4 light years is where we have Proxima Centauri, and it takes 60,000 years to go that far. Stars are very small, or on the scale of separation of stars in our galaxy, the stars are very small compared to the distance in between stars. So how do we determine the distance? A fundamental way of determining distance is the parallax method. This is not the only method, but it's a key method for finding distances. It is a very reliable method if your star is close enough where you can do the measurement. So to kind of get an idea of this, you should do this on your own. Put a finger in front of your face and then close one eye and then close the other eye, and you will see your finger appear to move compared to the more distant objects in your room. So that's the parallax activity. And in this process for astronomy, one eye represents the position of the Earth at a time of year. The other eye is where the Earth is 6 months later. Now, this measurement is very difficult. The Greeks did not observe any parallax. You cannot observe it with just your eye, and for that reason the Greeks thought that the Earth was moving and didn't understand that the stars don't shift back and forth in the sky because they're so far away. But let's go beyond that and into more parallax. So here's a semi-famous Midwestern university in Fremont, Nebraska. And standing here, I took this photograph, and I'd like you to observe the apparent position of this light pole. It's on the left edge of the planetarium, Lenin-Hainer Planetarium at this semi-famous university in Fremont, Nebraska. And I'm going to move 1.6 meters to my left and take another picture. And in doing so, you can see that this light pole appears to be shifted in its position compared to where the planetarium is. I'll go back. The first picture, the light pole is on the left edge of the planetarium. The second picture, the light pole is on the right edge of the planetarium. And by knowing how far I moved and measuring the angle, it would be possible with trigonometry to calculate the distance to this light pole. Now, in my astronomy class, we're not going to get into trigonometry and do those calculations. There's just a simple rule that we need to understand. But on the campus, another illustration here, another light pole, and I'm going to be moving to my left and taking pictures. And notice how the light pole changes in position, compared to, I picked the tree here as I was looking at it, and the light pole was on the left. Now from where this photograph was taken, the light pole appears to be on the right side. So again, try this. Put a finger in front of your face, close one eye, close the other, pretend that one eye is the Earth, and the other eye is the Earth in position in its orbit 6 months later. And if the stars were as close as the finger to your face, you would see a tremendous shift in their position over 6 months. The stars are much further away. You might try this by, again, moving your finger further away and closing one eye and then closing the other. And you'll see that your finger does not shift position as much as you move away. So here's the situation with the Earth going around the Sun. Astronomers can measure where a star is located on the star field compared to the more distant stars. Do that 6 months later. Take a photograph, take very careful measurements perhaps. But the shifting back and forth is called parallax, and it's due to not the star moving. The stars do move, but this effect of shifting back and forth over 6 months is due to the Earth's motion. This was first measured in 1838. It's a very difficult measurement. The parallax angle is very small. If you divide a degree roughly into 4,000 parts, you're getting on the order of the size of the parallax angle. And 1 degree, 360 degrees in a circle, divide the full circle by 360, that's 1 degree. Divide 1 degree roughly by 4,000, and you're getting to the scale of the parallax angle. A very difficult measurement, first done in 1838. Most locations would have a very difficult time measuring the parallax angle. For example, in Fremont, Nebraska, the sky quality is not very good, and our twinkling effect is about 3 times the parallax movement effect. So it'd be extremely difficult to measure parallax in this location. The twinkling effect really limits the ability for astronomers to measure the parallax for all the stars that are separate stars on the sky. But a handful of stars have accurate parallax measurements made from the Earth, and gave us a basis for the distance scale in the universe. Kind of a sidelight here. You need to know how many kilometers or how many miles from the Sun to the Earth. You need to know the astronomical unit. And that's sort of a separate determination I'm not going to go into in this video. You might look up some things about the transit of Venus, to get an idea about how astronomers worked out the distance from the Earth to the Sun. So once we do that measurement and stars that are different distances away will have different parallax angles. There is a relationship between the distance to the star and the parallax angle. Stars that are closer have a larger parallax angle. Stars that are further away have a smaller parallax angle. Or to say it a different way, if the parallax angle is larger, the star is closer. If the parallax angle is smaller, the star is further away. It's an inverse relationship. It's an inverse relationship. If the parallax angle is large, distance to the star is small. If the parallax angle is small, distance to the star is large. And there's a calculation that can easily be done. If you take the parallax angle to be p and measure this in arc seconds, the arc second is 1 degree divided by 3,600. If you take the parallax angle to be in arc seconds, divide that into 1, and you'll get the distance to the star in parsecs. Parsecs, so it's kind of a parallax arc second combination word, but parsecs. The parallax angle is 1/2 of the angle. It's the shift angle as the Earth goes through 6 months of its motion. And so if we would have a case of over 6 months, the total shift in angle is 0.4 arc seconds. The parallax angle would be 0.2 arc seconds. And the distance to the star would be 1 divided by 0.2. It would be 5 parsecs. A parsec is bigger than a light year, roughly a factor of 3. So we'd be talking, for this case, about 16 light years for this star. And the light year is a distance. The distance light travels in 1 year. Light takes 8.5 minutes to go from the sun to the Earth. So you should get a little sense here. The light year is a big unit. 8.5 minutes from the sun to the Earth, but a lot of minutes in a year, and that would be the light year distance. The closest star is about 4 light years away, the Proxima Centauri, this closest notable star. There may be some other very cool dim stars that aren't prominent in the sky, but about 4 light years. What about the brightness of stars compared to their distance? Well, as energy from a star moves outward, it's moving into a bigger and bigger sphere away from the star. This drawing just shows a section of the sphere, but it kind of gives you an idea. The energy that goes through a certain area, if we go out to double the radius away from this star, it turns out that energy would be diluted over 4 of these areas. If we go to 3 times further away, the energy that went through this 1 square back here is now going through 9 squares out here. So the energy is less concentrated, and to the eye, it's going to be less bright. In my class, we won't do calculations really with this, but the brightness is proportional to 1 divided by the distance squared. You should realize as things are further away, stars are further away, given that the stars are equal brightness, the star that's further away will be dimmer. And it turns out it gets dimmer faster than you think. It gets dimmer as the square of this distance to the star. But that's the brightness effect. So parallax, very important to measure the distance to the stars. Done in about 1838 for the first star. I don't know, hundreds or so, don't quote me on this, but from the surface of the Earth, kind of a small number compared to the number of stars have had their parallax measurements made. Fortunately, as spacecraft were put into use in general scientific research around the Earth, there was a spacecraft called Hipparchus, 1989 to 1993, that measured the parallax of thousands of stars. So why could it do better than ground-based telescopes? Well, in the space around the Earth, there's no atmospheric twinkling to distort the measurements. So the positions of the stars could be measured much more accurately and gave us thousands of parallax numbers and a whole catalog of distances to stars that greatly improved astronomers' knowledge of stars. So parallax allows us to calculate the distance to stars. A very important property for stars is to know how far away they are. We'd like to map out the universe, and to put them in the proper place in the map, we need to know their distance. And then to make certain measurements about the star as to how much energy it's producing, we need to measure its apparent brightness at the Earth, and knowing its distance, we could calculate the true brightness for the star, get an idea of the true energy being emitted from the star. Oh, you should keep reading about this and ask some questions of your instructor.